Let's do the problems of chapter number 8. Example number 5.1. Well, this is chapter number 5 from my personal book, and definitely chapter number 8 from the recommended book. So the magnetic flux density is given, which is 2e raised to power minus ZAX Tesla. Then find the flux passing through the following surface in AX direction. This is a constant X surface, and you know that the unit vector which is normal to the constant X surface is AX, and Y is changing from 0 to 2 while Z is changing from 0 to 4. So definitely the differential area of this surface will be equal to dy dZAX. The magnetic flux density is in the direction of the unit vector AX as well. So we calculate the scalar product of the magnetic flux density and the differential area. You see, the magnetic flux density is 2e raised to power minus ZAX. So the scalar product P dot ds result in 2e raised to power minus Z dz dy. We want to calculate the flux. So the flux can be calculated with the help of this integration. The integration of B dot ds gives you the flux passing through this surface in the direction of the unit vector AX. So we have 2, and then we have e raised to power minus Z dz, and then we have the integration of dy. You see, the integration of e raised to power minus Z is minus e raised to power minus Z, while the integration of dy is y. So we simplify this integration. We put the limits on the right hand side of this equation. So the magnetic flux passing through this surface turns out to be 3.93 Weber. Example number 5.2. Find the magnetic field intensity at 040 caused by the following source. The product of the current and the small length of the conductor is given, which is 64 into 10 raised to power minus 3 ampere meter, and this small current carrying element is located at the origin. So you see, the position vector of the point under observation is represented by R, and you see R will be equal to 4 AY. This is the position vector of the point under observation. The position vector of the small portion of the current carrying conductor will be R1, and you see R1 will be equal to 0 AX plus 0 AY plus 0 AZ. Anyhow, as we have considered a very small portion of the current carrying conductor, so the differential magnetic flux density will be equal to mu naught by 4 pi into IDL cross R minus R1 divided by R minus R1 raised to power 3. And you see R minus R1 is 4 AY. So if we put the values in this particular equation, the differential magnetic flux density will be equal to 64 into 10 raised to power minus 10 AX into 4 AY. And if we simplify this equation, the differential magnetic flux density turns out to be 4 into 10 raised to power minus 10 AZ Tesla. Well, example number 5.4, find the magnetic field intensity at this particular point in the rectangular coordinate system caused by a current of 24 pi ampere along the axis. So there is a current in the conductor, and the current in the conductor is in the direction of the unit vector AZ. The conductor is along the axis. The direction of the current will be given by the unit vector AZ. The conductor extends from Z is equal to minus 8 to Z is equal to 8. So let us consider the current carrying conductor. Here is the current carrying conductor. The conductor is extending from Z is equal to minus 8 to Z is equal to 8. Here is the point under observation. So definitely rho, which is the radial distance between the axis of the conductor and the point under observation, is 6 meter. Rho will be 6. So we will have to calculate alpha 1. You see the angle in the counterclockwise direction will be negative, and we will calculate alpha 2, and the angle in the clockwise direction will be positive. So we will consider these two angles. With respect to rho, the angle in the counterclockwise direction is negative, while the angle in the clockwise direction is positive. And in order to calculate the magnetic field intensity at the given point, we use this particular equation. So we use this particular equation to find out the magnetic field intensity at the given point. In this particular equation, rho is known. We need to calculate alpha 2 and alpha 1. So let us calculate alpha 2. Alpha 2 will be negative, while alpha 1 will be positive. No, alpha 1 will be negative, while alpha 2 will be positive. So you see, we calculate alpha 1. We calculate alpha 1. So for alpha 1, this side of the right angle triangle is 8, and this side of the right angle triangle is 6. So we have tangent inverse minus 6 by 8. 8 by 6. So alpha 1 will be equal to tangent inverse 8 by 6, and alpha 1 is minus 53.1. Let us calculate alpha 2. Alpha 2 will be positive. Alpha 2 will be positive. Why? Because alpha 2 is in alpha 2 is in the clockwise direction. So in order to calculate, you see this angle, the perpendicular of this right angle triangle is 8, and the perpendicular of this right angle triangle is 8, while the base of this triangle is 6. Okay, so here is the perpendicular of this right angle triangle, which is 8. So alpha 2 will be tangent inverse 8 by 6, and that is 53.1. So we put the values in this particular equation. You see the current in this particular equation is known, which is 24 pi ampere. Rho is known, which is 6. Alpha 2 is 53.1, and alpha 1 is minus 53.1. if we put the values on the right hand side of this particular equation, we obtained the magnetic field intensity at the point under observation. So the magnetic field intensity will be equal to 24 pi divided by 24 pi, and then we have the sine of 53.1 plus the sine of 53.1 into a phi. If we simplify this particular equation, the magnetic field intensity will be 1.6 a phi, and this magnetic field intensity is in the cylindrical coordinate system. This magnetic field intensity is in the cylindrical coordinate system. So in order to consider the magnetic field intensity in the rectangular coordinate system, we consider, you see this diagram. In this particular diagram, the conductor is along z-axis, and the point under observation is located on the y-axis. So if you apply the right hand rule at the point under observation, then the magnetic field intensity in accordance with the right hand rule will be in the direction of the unit vector minus ax. So we replace a phi in the answer by minus ax. So we replace a phi by minus ax, and the magnetic field intensity at the point under observation will be equal to minus 1.6 ax ampere per meter. We do example number 5.5. Find the current in an infinitely long conductor that generates a magnetic field intensity of 2 a phi ampere per meter along the circumference of a circle around the conductor. The radius of the circle of the circular path is 5 meter. So this is rho, which is basically equal to 5 meter, and here is the magnetic field intensity, right? So anyhow, we consider the Ampere circular law. The Ampere circular law says that the integral of the magnetic field intensity around a closed imaginary path will be equal to the current enclosed by the closed path. So if we consider a circular path of radius rho around this current carrying conductor, the entire conductor will be located inside the closed circular path, and it means that the current inside the closed path will be equal to the current in this conductor. Now the magnetic field intensity is given, which is 2 a phi ampere per meter. We consider the differential length vector along the circumference of the closed circular path. So the differential length vector will be equal to rho d phi a phi. So the differential length vector will be equal to rho d phi a phi, and as rho is 5, so the differential length vector will be equal to 5 d phi a phi, and then we calculate the scalar product of the magnetic field intensity and the differential length vector. So the scalar product of these two vectors will be equal to h dot dl, and h dot dl will be equal to 10 d phi. So we integrate h dot dl, and the integration of h dot dl will give you the current inside this closed circular path, and that will be the current in the conductor. So we put the value of h dot dl in this integration. So we have 10, and then we have got the integration of d phi, and you see that phi along this circular path of 5 meter radius is changing from 0 to 2 pi. So the integration of d phi results in phi, and if we put the limits, so we will get 10 into 2 pi. So the current in the conductor will be 62.8 ampere. Example number 6, find the integral of the magnetic field intensity around the closed path from A to B to C to D and then back to A. So this is a closed circular path. If the magnetic field intensity is 2AX plus 3 by X AY ampere per meter. So we need to calculate this integration, that is the integral of the magnetic field intensity around the given closed path. So we will have to calculate this integration, right? So let us consider the diagram. You see, here is A, which is 2, 0, 0, and then here is B, which is 2, 2, 0, and then here is C, which is 4, 2, 0, and then here is D, which is 4, 0, 0. So you see this is a closed rectangular path. So we will consider path K, and we will calculate the integral of h dot dl along this straight segment. Then we will consider the straight segment L, and we will calculate the integral of the magnetic field intensity along this straight segment. Then we will consider the straight line segment M, and we will calculate the integral of h dot dl along this straight line, and finally we will consider this straight segment N, and we will calculate h dot dl along this straight segment, and this will give you, you see, the integral of h dot dl. So then we will add the integral of h dot dl along these straight segments, which will give you the integral of the magnetic field intensity around this closed circular path. So let us consider path K. We consider the straight line segment, which is represented by K. So if you consider this straight line segment K, so you see X is constant over here, which is 2. Definitely dx will be equal to 0. Similarly, Z is 0 along this straight segment. Definitely dz will be equal to 0, and only y is changing from 0 to 2. So let us consider this straight line segment, which is represented by path K. So you see x along this straight segment is 2, so definitely dx will be equal to 0. Then z along this path K is 0, so definitely dz will be equal to 0, and only y is changing from 0 to 2. So definitely the differential length factor will be equal to dy ay, and we calculate h dot dl. So dl is dy ay, and h is given over here. This is h. So this is h. So if we calculate h dot dl, h dot dl gives you 3 by x it gives you 3 by x into dy. But x along this path is constant, which is basically equal to 2. So h dot dl will be equal to 3 by 2. So let us integrate h dot dl along this straight segment k. So we integrate h dot dl along this straight segment path, or the straight segment k. So we have 3 by 2, and then we have the integration of dy, and y is changing from 0 to 2. So the integration of dy is y. If we put the limits on the right hand side, then we get 3 ampere. So the integration of h dot dl along the straight path k results in 3 ampere. Then we consider path L. Let us consider path L. We consider path L. So you see y is constant along this particular path, which is 2. Definitely dy will be equal to 0. Z is constant along this path, which is 0. So dz will be 0. And x is changing from 2 to 4. So if we consider this straight path L, you see y along this particular path is 2, which is constant, so dy will be equal to 0. Z along this path is 0, so dz will be equal to 0, and only x is changing from 2 to 4. So definitely the differential length vector will be equal to dx ax, and we calculate h dot dl. So dl is dx ax. So h dot dl will be equal to 2 dx. H dot dl results in 2 dx. We integrate this h dot dl along the path L. So we integrate 2 dx, and x is changing from 2 to 4. The integration of dx is x, and if we put the limits on the right hand side, the integration of h dot dl along the straight line segment L results in 4 ampere. Let us consider the straight path M. We consider the straight path M. You see x along this particular path is 4, so dx will be equal to 0. Z along this particular path is 0, so dz will be equal to 0. Only y is changing from 2 to 0. So we consider the straight path M where x is 4, so definitely dx will be equal to 0. Z along this path is 0, so dz will be equal to 0, and y is changing from 0 to 2. So you see y is changing from 0 to 2. As y is changing only, definitely the differential length vector will be equal to dy ay, and we calculate h dot dl. So h dot dl results in 3 by x dy, and as x is 4, so we will get 3 by 4 dy, and we integrate this h dot dl along this path M, and we know that h dot dl is 3 by 4 dy, so 3 by 4 is constant, and we integrate dy from 2 to 0 because y is changing from 2 to 0. we know that the integration of dy is y. If we put the limits, the integration of h dot dl along this straight path gives you minus 1.5 ampere. Finally, we consider the straight path n. So let us consider the straight path n. You see y is 0, so definitely dy will be equal to 0. Similarly, z is 0, so dz will be equal to 0, and x is changing from 4 to 2. So along this straight path, x is changing from 4 to 2. Let us consider this path over here. We consider path n, where y is 0, definitely dy will be equal to 0, z is 0, so dz will be equal to 0, and x is changing from 4 to 2. So definitely the differential length vector will be equal to dx ax. And if we calculate the scalar product of h dot dl, the scalar product of h dot dl results in 2dx. So the scalar product of h dot dl results in 2dx. So we integrate h dot dl along this path. So we integrate 2dx, and x is changing from 2 to 4. And we know that the integration of dx is x. So if we put the limits on the right hand side, the integration of h dot dl along this path n results in minus 4 ampere. Now the integral of the magnetic field intensity along this closed path will be equal to the integral of the magnetic field intensity along path k plus the integral of the magnetic field intensity along path L plus the integral of the magnetic field intensity along path M plus the magnetic field intensity plus the integral of the magnetic field intensity along path N. And if we put the values on the right hand side of this particular equation, we get 1.5 ampere. So the magnetic field intensity, the integral of the magnetic field intensity around this closed rectangular path results in the current in the conductor, and the current in the conductor is 1.5 ampere. Well, in example number 9, we want to calculate the magnetic field intensity at 420, and which is caused by an infinite sheet of current. The infinite sheet of current is located in the x is equal to 0 plane, and the surface current density of the infinite sheet of current is 8 Az ampere per meter. We know that the magnetic field intensity at any point due to an infinite sheet of current is given by this particular equation. So the magnetic field intensity at the point under observation, which is caused by an infinite sheet of current, is equal to 1 over 2 k cross an. Now is this sheet is located in the x is equal to 0 plane, so the unit vector which is normal to the sheet will be the unit vector ax. So let us put the values on the right hand side of this particular equation. So you see k is 8 Az, so the magnetic field intensity will be equal to 1 over 2 8 Az, and an is ax cross ax. We simplify this particular equation, and the magnetic field intensity at the point under observation is 4 Ay ampere per meter. We do the last numerical question of this particular chapter. This is example number 8, which says that find the curl of the magnetic field intensity if the magnetic field intensity is 2E raised to power 2z AX ampere per meter. If you focus on the mathematical expression of the magnetic field intensity, this mathematical expression is in the rectangular coordinate system. So we consider the curl of the magnetic field intensity in the rectangular coordinate system, and we calculate the curl of the magnetic field intensity in the rectangular coordinate system with the help of this particular determinant. So we consider the unit vector AX, the unit vector AY, and the unit vector AZ in the first row of this determinant. Then we consider curly by curly X, curly by curly Y, and curly by curly Z in the second row of this determinant. And then we consider the X component of the magnetic field intensity, the Y component of the magnetic field intensity, and the Z component of the magnetic field intensity in the third row of this determinant. If you focus on the expression for the magnetic field intensity, you see the magnetic field intensity the magnetic field intensity has got one component only, and this component is the X component. So the X component of the magnetic field intensity is 2 e raised to power 2z. The Y component is 0 and the Z component is 0. There is no component along Y axis and no component along Z axis. So we put the values in this particular determinant. So we have the unit vector AX, the unit vector AY, and the unit vector AZ in the first row of this determinant, and then we have curly by curly X, curly by curly Y, and curly by curly Z in the second row of this determinant, and then we have the X component of the magnetic field intensity, and you see the X component of the magnetic field intensity is 2 e raised to power 2z, the Y component is 0, and the Z component is 0. So we expand this determinant, and the expansion of this determinant gives you the curl of the magnetic field intensity, and here is the curl of the magnetic field intensity. So the curl of the magnetic field intensity is 4 e raised to power 2z AY ampere per meter. So this is all we are supposed to do. Thank you so much. We will start chapter number 9 in the upcoming class.